Hello, welcome to our lesson on applications of solving triangles, where we will put into practice the formulas that we've been looking at over the past few topics. So this will give you hopefully an appreciation for the solving of the triangle process, because that is going to be the easy part of what we do today. So when we apply the use of these formulas to these word problems, the hard part is not using the formula or whichever formula applies. The hard part is drawing a picture so we understand what our triangle looks like. So you'll see that, and it really just takes practice. But before we get started, let's just do a little recap on the tools we have to solve. So if we're given a word problem, we can draw out the picture and we figure out that the triangle in our picture is a right triangle. That would be best case scenario, because for a right triangle we have all kinds of very familiar ways to solve. We know we can find missing sides using the Pythagorean theorem, so a squared plus b squared equal to c squared. We can also find missing sides or angles using our trig ratios. So we could say that the sine of an angle is equal to the opposite side over the hypotenuse. We could say cosine of an angle is the adjacent side over the hypotenuse. And we can say that the tangent of an angle is equal to the opposite side over the adjacent side. And why did I use lowercase on that one? I don't know. But now I need to go back and fix it. Okay, so if we have a right triangle, lots of ways to solve, lots of familiar ways to solve. Again, that would be best case scenario. Now, if we don't have a right triangle, but we are given or guaranteed, or we have a triangle that is determined by angle, angle, side, angle, side, angle, or the not guaranteed side, side angle, those will be the cases where we're going to try to use the law of sines in order to find our missing parts. And if we are given side, 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 or we're given side, angle, side, then we're going to try to use the law of cosines to solve. And for our reference, we have those formulas on the notes. Okay? So again, the hard part of this is going to be taking our situation, drawing a picture from it. Once we have the triangle, once we have the picture, the solving should be the easy part. Okay? So let's get right into this. I'm going to start off with a slow build. Hopefully some of the concepts will feel familiar. And again, putting into practice the new formulas, but with some situations we've seen before. So let's look at number one. We have a building downtown casts a 40.6 meter shadow on the ground. If the angle of elevation of the sun is 34.6 degrees, what is the height of the building? So remember, when we're looking at an angle of elevation or an angle of depression, it is an angle that is created by looking up or by looking down from a horizontal line of sight. So we have to have a horizontal somewhere, and then a line that goes up from there or down from there. Up if it's elevation, or down if it's depression. Okay? Now, in this picture, it should make sense that we have a horizontal because we have a building, and the building sits on the ground, which is our horizontal. So let's try to sketch this out. I'm going to put my building, and actually, I have this nice drawing tool, so I'm going to put my building here, and then here's going to be the shadow that is on the ground. So this is my building, and here will be the shadow of my building on the ground. Okay, so this building is casting a 40.6 meter shadow. So on the ground here, I can call this 40.6 meters. And it says that the angle of elevation of the sun is 34.6 degrees. What is the height of the building? So the height of the building is my unknown. So I'm going to call this side x, and you can call it whatever variable you want. And if you wanted to put more into the picture and then determine what variable you want, so you just want to call this a question mark, whatever makes you happy. And if nothing makes you happy, I'm sorry, you're just going to have to pick something. Okay, so the last piece of this triangle, I mean, there's really only one place for the side to go, but it should make sense. If we have an angle of elevation, again, it's an angle that's created from a horizontal. So the ground is our horizontal. That means the angle has to be created from that horizontal. So our angle of elevation has to be this third side of the triangle. Okay, and that, again, should make sense, not just because it's an angle of elevation, but because we have the building casting a shadow. That means the sun would be over here, right? It's got to be behind the building for the shadow to be on the ground. If you had the sun shining from over here to the building, it's not going to create that shadow, all right? So there's our sun, there's our angle of elevation at 34.6 degrees, and it should be pretty clear what we're going to use to find that missing side of this right triangle. Of course, our building is going to be perpendicular to the ground. This is not the leaning tower, okay? So since this side that we're looking for, I called it a question mark, but now I'm going to go back and put it in as a variable. It is opposite of the angle that we are given here. This side is adjacent to the angle that we're given, so all we need to do is use tangent. The tangent of our 34.6 degree angle is going to be equal to a ratio of that opposite side that we're looking for over the adjacent side, and I don't like to use, I called it O. I'm going to stick with X. It is the opposite side. So if you want to keep, sorry, I'm using too many colors. I'm going to call this X. If you want to still keep your labels on here as the opposite and adjacent, that's fine. It's just the O in the formula or in the equation makes it look like a 0, and I don't want to mess that up. So tangent of our angle equal to the opposite side, X, over the adjacent side, which is 40.6. So to solve for x, all I have to do is multiply that 40.6 over. So x is going to be exactly 40.6 multiplied by the tangent of 34.6. And then from here, it's an approximation with our calculator. And let me get that calculator going. Alright, let's make sure our calculator's in degrees. So we want to know what is 40.6 multiplied by the tangent of 34.6, and there it is. It's approximately 28-ish. So it's about 28.01. The problem doesn't specify where to round, so I think the hundreds place is generally pretty standard place to round. And even if you wanted to call it 28, I'd be good. Now these are meters, so if you wanted to say about 28 meters, I think that would be a pretty reasonable answer. Okay, first one down. The easy one, down. Okay, done and down, done. Let's move on to the next one. And I'm just going to warn you, like, that's the only one that makes a right triangle. The rest is going to involve more of what we've been working on in the last few topics, because our law of sines and law of cosines. So, number 2. A ship is sailing due north. At a certain point, the bearing of a lighthouse 7.6 kilometers away is north 38.4 degrees east. Later on, the captain of this sailing ship notices that the bearing of the lighthouse has become south 33.4 degrees east. How far did the ship travel between the two observations of the lighthouse? So we have bearing in this problem. Bearing, remember, if we're given one measurement, so if I just set a bearing of 38 degrees, we are always going from due north, and then we would go clockwise, however many degrees. If we are given a bearing that has two measurements, or two directions, I mean, so this one says north and then 38.4 degrees east, so we start as like the north as our initial side, and then we would go east with our angle. If it was south, we would start south, and then like this one is south then east from there. So hopefully we remember some of that, and you can dig back into your notes from Module 1 if you need to. But let's try to draw out what's happening. So initially here, our ship is sailing due north. So I'm going to start by just making this north-south line. Okay, so we're due north. Ship, oops, I got my draw tool on. My ship is on this line somewhere. Okay, and it says that at a certain point on this trip, the captain is spotting a lighthouse 7.6 kilometers away, and it's north 38.4 degrees east. So at some point on this trip, let's just call it A, it's going to spot a lighthouse, and I'm going to put that lighthouse out here. So some point on the trip, it sees a lighthouse, and I'm not going to try to draw it because you've seen my artwork is terrible, so I'll just call that a lighthouse. Alright, so here's our ship, where it starts. Okay, sees the lighthouse, and I know that, I guess maybe you don't know why I put the point out there, but it says the bearing is north 38 degrees east. So from my north, if I went a full 90 degrees, whoops, that's my eraser. If I went a full 90 degrees, I would land here. If I want to be 38.4 degrees in the east direction, then I'm going to be looking something like this, okay? So let me, actually I could put that out there if I want. So I'm going to call that east. So my lighthouse, again, 38.4 degrees, something like this. Lighthouse is going to be out here, okay? So let's call this the lighthouse. And again, it's 7.6 kilometers away. And this was a 38.4 degree north, 38.4 degrees east angle. Okay? So there is the first part of it. We're sailing due north, and we've got this component taken care of. Now this ship still traveling due north. At a later point, it spots the lighthouse again, but the bearing has changed. So later, then maybe change colors. It says later, the lighthouse has become, the bearing for the lighthouse has become south 33.4 degrees east. So later on, some other point in this trip, maybe I need to go a little bit higher just to make a triangle out of this. The bearing is south, so now we're on this south line, but we're also again headed east by 33.4 degrees. And it should make sense that we're going to go this way because it's the only way to make the triangle out of this picture. But again, the angle that's going to be in here is going to be 33.4 degrees. And we don't know how far that one is, so I don't know that distance, but that's okay. Now we go to our question. What's the question? What are we trying to find? It says, how far did the ship travel between the two sidings? So remember, the ship is traveling on this line. And so that is the question here. That is what we are trying to find. Okay? So I don't know what you, if you were doing this on your own, what you would use for labels, but I do like A, B, and C. We're pretty used to using those, and since that's what our formulas relate to. Let me go ahead and call these points here A, B, and C. Then this would be side A, and then what we're looking for here would be side B. Okay? So do we have enough information to use, well, it's not a right triangle, right? Do we have enough information to use the law of sines? Because if we do, that would be the easiest case. And I don't know if we do in this. Let's see, we have an angle, and then a side, but I don't know if we have the right angle if we're going to try to find side B. However, it wouldn't be too hard to go ahead and find angle B since we know the other two angles in the triangle. So I'm going to do that first. If I wanted to find angle B, we have 180 degrees. Let's subtract out the 33.4 degrees and the 38.4 degrees that are already in the picture. So 180 minus 33.4 and 38.4 leaves us 108.2 degrees for B. So 108.2 degrees. So let's put that here, 108.2 degrees. And now I think the law of sines is going to be great. So I can write a ratio that uses the sine of A and side A and the sine of B with side B and find that unknown piece. So let's do it. Since I'm solving for B, I'm going to put that on the top of my fraction. B over the sine of B, which again is 108.2 degrees, has to equal A, which is 7.6, over the sine of A, 33.4 degrees. Now I'm going to multiply both sides by the sine of 108.2. So B is exactly 7.6 times the sine of 108.2 degrees divided by the sine of 33.4. And now the really easy part. Let's make sure we can approximate this with the calculator. Make my fraction on the top. 7.6 times the sine of 108.2, and then the sine of 33.4, and again, make sure we're in degrees. Yep. So B is going to be approximately 13.12-ish, and that is, in this case, kilometers. So the ship has traveled 13.12 kilometers from where it started. So we can figure that piece out just by knowing the bearing on two sightings of a lighthouse off in the distance. Okay? Super pertinent. Real world application. Yes, I know. Alright, so let's keep moving along. We've got a right triangle, a law of sines. I bet you can guess what's going to happen in the next one. So number 3, a surveyor wishes to find the distance between two inaccessible points A and B on opposite sides of a lake. While standing at a third location, point C, she finds that her distance from A is 259 meters, her distance from B is 423 meters, and angle ACB measures 132 degrees 40 minutes. Find the distance between A and B. Alright, it's a lot going on here. So back to the beginning of the problem, a surveyor wishes to find the distance between two inaccessible points A and B that are on opposite sides of a lake. Okay, so I'm going to call this my lake. Obviously, there aren't going to be lakes that are perfectly shaped like this, but let's just pretend, okay? Because I have this nice draw tool. So points A and B are on opposite sides of the lake. So I'm going to put point A over here, and I'm going to put point B over here. And then it says that this surveyor is standing at a third location, point C. So she's not going to be standing on the lake, so she's outside of the lake. Let's just say she's here, okay? It says, so her location is point C. She finds that her distance from A is 259 meters. So then we know her distance from A is 259. So this distance right here, I can call that 200. Oops, my drawing tool is still on. 259 meters. And then it says that her distance from B is 423 meters. So her distance from B, that's this piece here. Again, 423 meters. And then it says that angle ACB. Now, I don't know how much. Well, I don't even know if we have seen an angle labeled this way, but this is the proper way to label an angle. Like when I say angle C, you know which angle I'm talking about, but generally, when we label an angle, I guess not generally, we do this both ways. We can use one capital letter for the angle, or if we wanted to use three letters, the three that we see in the picture here, the two points along the rays of the angle would be included, and then the point at the vertex would be included. When you see the three points used to label an angle, it's the one in the middle that contains the vertex. So angle C is really what we're looking for. The one in the middle is telling us specifically the corner or the point we're using for the vertex of the angle. So ACB is this angle here. Oops. That's 132 degrees 40 minutes. So 132 and 40 minutes. And somehow I managed to erase my point A. Okay, so the last piece is asking to find the distance between A and B. Again, that's the third piece of the triangle here, so it should make sense that that's what we're looking for. So what are we going to use? Okay, not a right triangle, and obviously my picture is not drawn to scale because I don't know if that really looks like a 132 degree angle in there, but nonetheless, what we're given in this picture is a side, or actually two sides, and an angle that is included. So if I have side, angle, side, remember this is a situation for me to use the law of cosines. And because I am looking for this distance here, little c, and I know the angle that's across from it, the only angle I have in this picture is angle C, I know to use the version of my formula that has angle C in it and starts with side C. Again, that's the one I'm looking for. So my formula says c squared is going to equal a squared plus b squared minus, oops, I forgot my 2, 2ab times the cosine of c. So that means c is going to equal the square root of all of that. And all of that being, A is over here across from angle A. That's 423 squared. Plus B across from B is 259 squared. Minus 2 times, again, 423 and 259. And then finally the cosine of 132 and 40 minutes. And that's 40 out of 60 minutes in the hour. So we want to make sure we capture that piece in there. If you're using your scientific calculator that has a minute key, awesome. If not, remember 40 out of 60 to get that fractional part. And now calculator work. So let's see if I can't not screw this up. 423 squared and 259 squared minus 2 times 423 times 259 times cosine of 132 plus 40 out of 60. Boom. 628 point, let's just say 110 technically, and we're good. So 600 and somehow I got a much different, I don't know. I think I rounded on my, I did some work on the side over here and I think I rounded way too much. Alright, so 628, which seems reasonable. 628.1, what are the units here? Meters. Or is it miles? Meters. Okay, meters. Done. And this picture wasn't entirely difficult to draw. Okay, so we got one example of each now. We did a right triangle, we did an oblique triangle using the law of sines, we had an oblique triangle here using the law of cosines. Let's see what happens on the next one. Two rangers. They're on an east-west line 110 miles apart. A forest fire is located on a bearing north 42 degrees east from the western station at A, and a bearing of north 15 degrees east from the eastern station at B. To the nearest 10 miles, how far is the fire from the western station? Okay, so first, two stations on an east-west line 110 miles apart. Let's draw that. East-west line, west being over here, east being here. Two rangers are on this east-west line, so let's put one over here. The western station is A, and it says the eastern station is B, and these two stations are 110 miles apart. Okay, first part of the picture, boom. It says there's a forest fire located on a bearing of north 42 east from the western station, and it's a bearing of north 15 east from the eastern station. So we have to try to figure out where this fire is. Now, it says it's north and east of both of these, so since it's east of not just A, but also east of B, I'm going to put the fire, like, out here. Maybe, let's use orange for the fire. I know, clever. Okay, so here's my fire. I'm not going to draw it, I'm just going to say this is my fire out here. It says from B, back to my presets, we're north 15 degrees east from B. So B, if I put a north line on here, okay, north and then east about 15 degrees, this is where we're going to go, okay? And that's why I put the point out here anyway. So this little angle in here is 15 degrees. And then it says from A, again, the north line, right? This time we're going to go 42 degrees east to get to that fire. So again, making the point up where I put it hopefully makes sense. So this angle in here is going to be 42 degrees. And now we have a triangle created. Now my triangle looks like poo because I didn't use my drawing tool, but don't judge me. Okay, so we got everything we need. We got our triangle. However, let's see. We don't have any other, it says, what's the question? From, or to the nearest 10 miles, how far is the fire from the western station? So the question in this one is this side length of our triangle. That's what we're going to be trying to find. Right now I don't have any of the angles inside of my triangle, and I don't have, if I had side, I could, that wouldn't be a problem. But it's a problem because I don't have that. I'm in fact looking for one of my sides. Before I can decide what formula to try to use, let's see if I can't find some of the angles in the triangle. So here, let's start. start over here, right? We have total 90 degrees between that north, south, and east, west line. So if I take the 90 and subtract out the 42, that's going to leave me 48 degrees for this angle inside of the triangle. So I got one down. And then let's see, again, this is my north line, and this is a 90-degree angle here. If I add in the little 15 to the 90, then this total angle, 90 plus 15, would have to be 105 degrees. So this total angle is 105. And now I could subtract those from 180. So 180 minus 105 and minus 48 leaves me, what, 27 degrees? I just better not. 180 minus 105 is 75, and then I take 48 away, and yeah, 27. Good. Sometimes I can actually do math. Okay, so 27 degrees is going to go here. And now I have all three of the angles. I have one of the sides. If I have two angles, remember, two angles and a side, whether it's angle, angle, side, or angle, side, angle, I should be able to use law of sines. So I'm going to do it. Technically, this missing side is across from b, so let's call it little b. So that's the one I'm trying to solve for. We'll say b over the sine of angle b, which we figured to be 105 degrees, is going to equal, I'm going to have to use, let's call this point up here c, and then this would be side c that goes across from it. We're going to have to use that pair since I don't have the one that's across from a. So let's go with 110 miles over the sine of 27. So that's c over sine c. And multiply both sides by sine of 105. So exactly 110 times the sine of 105 divided by the sine of 27. That's our exact answer. And then approximately, the calculator says, let's find out. A fraction 110 times the sine of 105 in the top and the sine of 27 in the bottom. So we have about 234.04-ish is what the calculator gives us. Now normally I'd box that in, but this one specifically says where to round. It says to the nearest 10 miles, which means I want to round in the tens place. And since after the 3 I have a 4, that 3 is not going to go up. So this is going to round to about 230 miles. Okay, we did it. One left. And I'm just going to guess. I don't have to guess because I made these problems, but if I had to guess as a student, right? One right triangle, got one easy one. We had a law of sines, law of cosines, law of sines. This is probably going to be a law of cosines problem. So let's try it, and actually I saved the best for last. It's challenging, I'm not going to lie. Let's try it out. An airplane flies 180 miles from an airport at a bearing of 125 degrees, and then it turns and flies at a bearing of 230 degrees for 100 miles. How far is the plane from the airport? Okay. So we have, sorry, my pencil thing fell. An airplane flies 180 miles from an airport at a bearing of 125 degrees. So let's call this point A. Let's call it the airport. Oops. If my pen would go. So let's call this airport point A. Okay, a plane is going to fly 180 miles from that at a bearing of 125. So remember, our bearing with just the angle measurement given here, not northeast or southeast or whatever, we always start from north and then we go clockwise 125 degrees. So if I was to put a north line on here, right, let's put a north-south line on here, I would start here. Actually, I need another one, east-west too, so I can. If I started here and went, this would be 90 degrees. I want to go 125 degrees, so not quite to my south, right, because that would be 180. So then I'm going, this is my bearing, and I'm going this far, it says for 180 miles, and then I stop. So let's just call this 180 miles. And this angle up here, again, was 125 degrees. Okay, so then from there, the plane, it turns, and then it's flying at a bearing of 230 degrees. So at this point, it makes a turn. Let me just draw in my north-south from here and east-west from here. It turns, and the new bearing is 230 degrees. So again, I would start here. I would go 90, 180, and then not quite to 270. So 230 is going to be like here. And I'm going to go here for 100 miles. So let's call this 100 miles. And the question now is, how far is the plane? This is where the plane is ended, gone the 180, then the 100. How far is it from the airport? So how far is the plane from the airport? This missing piece of the triangle is the piece I'm going to be trying to find. And for labeling purposes, let's go ahead and call this B over here. We can call this C, which means we're going to be looking for little side B. I do not have enough information to be able to solve yet. I know two sides of my triangle, but it's not a right triangle, so I can't just use Pythagorean theorem. If I could figure out the included angle, then I have side angle side. I could use my law of cosines, but let's try to see what we can do about these angles, okay? So, where do we start? If I wanted to know, I need another color. Let's go back to orange. This angle in here, like if I wanted to find this angle, again, I could have my side angle side, and I could use my law of cosines to solve. But how do I get that angle? So let's go back to this red line, okay? If I extended this red line here, then what you can see is I have, oh, I don't have enough colors. How about purplish? So where I have this 125 degree angle, if I go all the way to the extension of that red line, I have a straight line. So if I took 125 away from 180, that means this little angle in here is 55 degrees. And the reason I put that there is because that means this angle here has to be 55 degrees, right? Because it's the same north-south. It's the same line on the north-south. So if that's 55 degrees, and let's see here, how much do I have? Well, this is, let's see, this was 230, right? This one is given to us as 200, oops, can't write, 230 degrees. And then I have another 55 degrees in there, in here, right? Then I can figure out exactly what's going to be left for the angle inside. So outside of that angle, again, I have the 230 degrees plus I have the 55 degrees. If I take that away from the full circle, then I should have left over the angle that's inside of my triangle. So what's 180? What's 360 minus the 55 and the 230 is 75 degrees. So this angle in here is 75 degrees, and now we are in good shape. Because again, I have side, angle, side, and I have enough to use my law of cosines to solve. And that was a tough one, that picture, getting all those angles in there, but hopefully it makes some sense. Now let's try to solve. Since I'm trying to find b, little b, and I have angle b, I have to use the version of my formula that starts and ends with b. So b squared is a squared plus c squared minus 2ac times the cosine of b. So b is going to equal the square root of a is 100 squared, c is 180 squared, minus 2 times 100 and 180 times the cosine of b, which we figured was 75 degrees. I said we figured because I know you were doing this along with me, right? And now I just go to the calculator and ask it to approximate. So the square root of 100 squared and 180 squared minus 2 and 100 again and 180 again, and then cosine of 75. 181.89-ish, And again, it doesn't specify where to round, so this is going to be perfectly acceptable. And we'll say miles to make this a little more precise, and we did it. Okay, we survived. Again, I'm saying we, assuming that you've made it to this point in the video. If you have not, I am talking to myself, but maybe you have. Maybe you need to watch again. I don't know. The homework problems that I put in your assignment, they should align pretty well to these problems. Again, the hard part is drawing the picture. Again, the homework problems that they align, they really should be almost the same picture. But this should help you, like, try to draw the picture on your own and then look back at the ones we did in the notes, because they are going to be very, very similar. Okay, so hopefully this is enough to get you going, but as always, if you need help, just reach out. Until next time, take care.